This video briefly describes the various issues specifically related to power system protection that one needs to consider while implementing high penetration of solar photovoltaics or PV in an existing or a new distribution feeder. Here I will just present a list of potential protection related issues with high penetration. First is the ratings violation. Now, when PV inverters inject current during a fault in the feeder, that adds to the existing fault current available from the grid, and there is a possibility that under very high penetration scenarios, the ratings of the fuses or the interruption current rating of the reclosers or breakers are exceeded. Second is the loss of coordination. The protection devices like fuses, reclosers, and breakers, they are designed to clear faults, and their settings are selected to achieve minimum service outage for both short or temporary faults as well as for longer, more persistent faults. Now, this coordination is done based on calculation of fault currents from only the substation under no PV, the base scenario. But the addition of the distributed inverters fault current, and especially when they are non-uniformly added among the different protection devices, now that can lead to loss of coordination, meaning a device that is supposed to provide backup protection may actually end up operating before the primary protection for a particular type of fault, and that can lead to a larger service outage than necessary. Next is the so-called sympathetic tripping. Now, this is a nuisance issue that arises when a protection device like a recloser, it operates for a fault not in its own zone of protection, but for a fault in an adjacent feeder. And this can happen due to the fault current from the inverter in its own zone, but in the reverse direction. Next is the reduced sensitivity or the reduced reach of a feeder recloser or a substation relay. Now, it may initially sound surprising, but the fault current seen by a recloser or a relay may actually decrease because of the fault current from the inverters. This depends on the location of the PV system, downstream versus upstream, and so on, and we'll see some examples of that. But this reduction in fault current seen by the relay, it reduces its sensitivity to detect remote faults. The next two issues, namely the neutral current and the inverter grounding issues, and then the risk of unintentional islanding, these are related to protection, but not in the sense of device coordination and settings. The neutral current in the system can increase if the installations of single-phase PV systems, if they are not balanced among the three phases. The higher neutral current may impact some of the ground pickup current settings and so on. And also the way the PV systems are grounded can have a big impact on grounding related overvoltage issues. The islanding issue is that if by a remote chance you have a perfectly matched load and PV generation, and the inverter's anti-islanding or island detection schemes have failed for some reason, then we have a potentially dangerous safety issue where a section may be assumed to be de-energized from the grid, but it is actually energized by the local PV generators. Since the last two issues, they do not involve traditional coordination related protection analysis, we will not discuss them anymore in this video. But these are certainly important issues, and we may take them up in a different video, especially the unintentional islanding. So in the rest of the video, we will look at the first four issues in slightly more detail, starting with the ratings violation. Now, before we get into these four issues, I need to clarify some points about the behavior of PV inverters during faults. The reality is that very little is known about the inverter fault current characteristics for different types of faults. and they also vary a lot from vendor to vendor. Unlike the conventional generators, the fault current characteristic of a PV inverter is a strong function of the controller design, which is proprietary. So in the literature for protection analysis, several assumptions are made which, as one would expect, are not uniform across all the studies. The fault current values cited in the literature, they range anywhere between 100% to 200% of the inverter rated current. So in our study, as a worst case, we assume a 200% inverter current rating as the fault current contribution. Now, a point to note here is that it is 200% of the inverter's rated current, or the current at inverter's rated power, which often can be quite higher than the power rating of the PV arrays. And the inverter can also source this rated current during faults, even under low solar irradiance, because during faults the grid voltage is low, and so the real power needed at this low voltage for a given current is also low. Then the duration of the inverter fault current is another big unknown. Values in the literature vary from less than 5 milliseconds to as much as 2 seconds, which is the IEEE 1547 limit to disconnect when grid fails to prevent islanding. Also, per current standards, for voltage dips between 0.5 and 0.88 per unit, the inverters can remain connected for 2 seconds. Now, for remote faults, the voltage dip may not be less than 0.5 per unit. So there is a good chance that the inverters remain connected for 2 seconds. And also with the emerging requirements on grid support functionalities, especially for the utility scale inverters, like the low voltage right through LVRT, this typically makes the inverter remain connected for longer duration during faults. So it is reasonable to assume 2 seconds as a worst case value. Now, in most fault cases, 2 seconds is long enough for many of the protection devices to operate. So in this study, we assume that for the entire duration of fault analysis, the inverter remains connected and sources about 150 to 200% of the rated current continuously. Consider this simplified feeder with a fault at this location. The fuse current I fuse 1 in the base case is the fault current I sub from the substation, which can be calculated using the impedance up to the fault location. The fuse rating itself is selected based on the maximum fault current seen in this branch. Now to this, if we add these distributed PV generators, each producing fault currents like IP1, IPV2 and so on, then clearly the total fault current through the fuse 1 will increase. So the magnitude of the fuse current, I fuse 1 magnitude, is now the magnitude of sum of all the current contributions, including I sub prime, which is the new fault current from the substation in the presence of the PV inverters, and the sum of all the PV currents themselves, their magnitude. So that is larger than the original I sub or the I fuse current magnitude. Now, if this increase is significant enough under some hypothetical very high penetration scenario, or if the fuse rating already had very little margin to begin with, then we have the potential for the fuse rating to be violated because of these distributed PV generators. Also note that the fuse current magnitude is not simply the sum of the magnitudes of the substation and PV currents. This is because of the phase angle difference between the substation and the PV inverter currents. the substation fault current lags the grid voltage by 90 degrees because the fault impedance is predominantly inductive. Whereas the PV injected current, especially for the smaller residential rooftop PV, the current is controlled to be in phase with the voltage. So the two fault currents, the substation fault current and the PV inverter fault current, they add in quadrature, and because of that, the increase in the magnitude is not that significant. So the impact of residential rooftop PV in terms of this particular issue, that is the rating violation issue, is not very significant, and one can mainly focus on utility scale PV systems for the device rating violation issue. Also, I have mostly been talking about the fuse ratings, but clearly in this example, the current from this PV1 increases the fault current through the recloser for this fault here. So if the PV1 system happens to be relatively large, then once again we have the potential for the recloser rating also to be exceeded. Okay, next let's discuss this issue of sympathetic tripping. So consider the fault shown here in this branch. Now to clear this fault with minimum service outage, fuse 1 should clear, or it should coordinate with this recloser. Clearly there is no fault in this neighboring branch, therefore fuse 2 should not operate. But because of this presumably large PV system, which feeds fault current in this direction through fuse 2 into this fault, because of this large current, there is a possibility that fuse 2 also clears, taking out this entire branch unnecessarily. So this is called as the nuisance or the sympathetic tripping. Now, probably this is not a likely scenario at the expected values of high penetration. So that is because the fuse current, the fuse ratings are several times larger than the maximum load current in that in that branch. So for the PV current to exceed the melting current rating of the fuse, its rating needs to be several times higher than the maximum load in that branch, which is probably an unlikely scenario. Another scenario for sympathetic tripping, which is often given in the literature, is as shown here. So we have a high penetration feeder, the feeder at the bottom, with the PV system ratings well above the maximum load in the feeder in our hypothetical situation. Now, when a fault occurs in this adjacent feeder, feeder 2, obviously only breaker 2 should open and breaker 1 should not. But because of the large reverse current from all of these PVs in this direction through the breaker and feeding into the fault here, this large reverse current may trip the breaker 1 as well, and that will take out the entire feeder 1. Now, if such a possibility is even considered, then protection devices are relays with directional capability, which will not operate for reverse fault currents are needed. Okay, so we will have to take up the discussions on loss of coordination and the reduced reach of recloses and relays in the part 2 of this introduction video.